My name's Didier Pettinga. I'm a technical director with Holmes Consulting Group based in Christchurch, and I was the principal structural engineer for the retrofit and strengthening of what was the Commerce Building and is now Rehua, the Education and Human Development Department.
Yeah, I'll introduce myself too. My name is Killian Kraus. I'm part of a small undergraduate research group at the University of Canterbury. I'm working for QuakeCoRE, which is a Centre of Research Excellence working on earthquake research here at UC. And what are the things that you did in this part of the building to make sure it's safe?
It's safe now. Well, the first thing was that because of the damage to the trusses that are above us here that were originally in the atrium, we completely removed all of the glass roof. Okay, so it was completely opened and all of that structure was removed. The only bits that remain from that, aside from the bridge over here and these two concrete stubs that support the new columns, that's all that remains. The rest was completely removed. And so that allowed us then to actually rebuild the atrium. And you can see now in here that there's all of this cross bracing in the roof plane. That cross bracing is taking all of the atrium load back to this corner over here. Right. Now, in front of us here is this diagonal brace. Okay, it's a steel tube, which is actually filled with like a concrete grout. Okay, so it's a fine concrete grout. And buried inside of that concrete grout is a steel plate, and that steel plate is connected at each end. The outcome of this is a very high performance brace element, okay, and we call that a buckling restrained brace. And the reason that it's called that is that the steel bar, which is actually the mechanism for resisting the earthquake forces, is prevented from buckling, okay, and typically when you compress those and you put them into a compression force, they want to bow, okay. It's something similar to, you know, pushing on a ruler or something like that. It bows out of plane. So by creating this concrete-filled tube with a bar inside it, you now have a buckling restrained mechanism that can absorb the earthquake energy as the building starts to sway. The other one that's over here is another type of brace. In this case, it's actually what we call a fluid viscous damper. And it looks very similar, but in size, it's definitely bigger. And the actual real mechanism of it is this part here, okay? And this is where all the action happens. These dampers are filled with a silicon fluid, and they act much the same as the shock absorber in a car, or maybe even the door close. When you try to close some of these doors, they have a soft close on them. And you find that the harder you push that close, the harder it pushes back. And that's because it's got these types of fluid dampers in them. These are much more expensive than the buckling restrained braced frames, but they are much more efficient, and they're the sort of thing which you can reuse over and over again.
How do these dampers dissipate the energy?
So you can imagine that you've got a chamber inside of them which is filled with this silicon fluid, and there's basically a piston shaft which moves through that fluid, and it's got a big disc through it. And as it moves, it's forcing the fluid to move from one side to another. And so that action of forcing this very stiff fluid to move creates heat, and that heat is the means to dissipating the energy. And at this level, down at ground floor, it's not a particularly big amount of movement. We only have to accommodate maybe 100 millimetres of movement at absolute most. But as we go up the building, you can imagine that the two buildings, they want to sway different amounts, okay? And we've got to allow for the fact that you could get these two buildings that have quite different characteristics during an earthquake. They may sway together, and we want to stop them bumping up against each other. So at the top of the building, the seismic gap, which you typically see as just a steel plate in the floor with a rubber gasket around it, that movement joint at the top is about 600 millimetres. Okay? So you can imagine the two buildings moving together or moving apart from each other. That's the range of movement we've got to accommodate.